Thank you for coming out to our screening of Blade Runner: The Final Cut. Is this anyone's first time seeing the film? Wow, okay. Is this anyone's first time seeing the final cut who has seen previous versions? All right, very cool. All right. My name is Bob. I am the Director of Programming here. I'd like to welcome you to the Colonial Theater. Thank you for braving the weather, and also kind of for proving me right, that people would come out no matter what the weather was like for Blade Runner. I really appreciate that. Okay, so tonight we are doing something special. It is our Science on Screen presentation of Blade Runner. Now, what is Science on Screen? Science on Screen is a grant-funded film series, and it's made possible by the Coolidge Corner Theater Foundation with a generous support from the Alfred P. Sloan Foundation. It features creative pairings of current films, cult films, classics, and documentaries. It has lively introductions with notable figures, and it is all from the world of science, technology, and medicine. So we are proud to be the only theater in the Philadelphia region that offers Science on Screen. This is going to be our 6th year doing this. Now, thank you. But I would applaud that woman right over there, Emily. She's the one who writes all the grants and gets us all this great stuff. Thank you, Emily. We will have 2 more presentations this year. We don't have the films quite ready to go to announce them, but there will be 2 more presentations similar in this nature. Now, the question tonight is, are we destined for dystopia? Rick Deckard's job, that's Harrison Ford, as a Blade Runner in the year 2019 is to track down bioengineered humanoids, or replicants. We don't yet live in this dystopian future of synthetic humans and space colonies, but could we? What is artificial intelligence already capable of, and what might AI look like during our lifetime? And you're going to see some of that later. Our speaker is Matthew Malencia. He's a Ph.D. candidate at GRASP Lab at the University of Pennsylvania, and he will answer those questions after the film. So when the film is over, we are going to set up the stage, the podium, the mics, and everything. We're just going to turn the music down, we'll set it up, and then we'll begin when Matthew's ready. So I invite you all to turn off your cellular devices, because you just bought a ticket to not only watch a fantastic film that will leave you breathless at the end and hopefully crying, but you've also got a ticket from the internet, a vacation from your cell phone, from the rest of the world. You can turn off your brain and just enjoy this fantastic film that asks so many questions about the future, humanity, AI. Thank you. Absolutely. Enjoy the film. All right. Is everybody ready? Yeah. All right. Okay. Well, what an amazing film. And to see it big, you always see so much more. You'll see all those little details, you see all the little logos. When it's on your TV, as big as your TV is, it's not as big as that screen. And it's just amazing. And the music, the lights, the sound, everything. That movie is timeless. And it's the 40th anniversary of Blade Runner. So it's just amazing that we could actually show it and got it in here. Now, we are going to have a discussion. So our speaker today is Matthew Malencia, Ph.D. candidate at GRASP Lab University of Pennsylvania. He is a robotics researcher, an AI educator, and a science policy advocate. He is pursuing his Ph.D. in electrical and systems engineering at the University of Pennsylvania with advisors Dr. Vijay Kumar and George Pappas, and is a visiting researcher at the University of Cambridge with Dr. Amanda Prorok. His research focuses on fairness and diversity on robot teams. Matthew is the co-director of AI4ALL at GRASP, a summer program that teaches Philadelphia area high school students the fundamentals of artificial intelligence and robotics. Lastly, Matthew works with the Science Policy and Diplomacy Group at the University of Pennsylvania on AI ethics and policy. He has written multiple AI memos, engaged with policymakers on all AI topics, and during a science and technology forum, delivered an intervention on the floor of the United Nations. Please join us in giving Matthew a round of applause and a welcome.
Hey everyone, thanks for being here. By a show of hands, who here saw Blade Runner tonight for the first time? Awesome, cool, did you all like it? Yeah, cool. So I love these kinds of movies because I think they don't tell us as much about AI as they tell us about ourselves. And they're really, philosophical about humanity and about life. So what I want to do with this talk is actually take us from the philosophical to the tangible and talk about what AI is today in the real world. So by a show of hands, who here has interacted with AI, artificial intelligence, in the real world? Okay, I see some hands, most of the hands. Whether you know it or not, you should all have your hands up. You might not know it, so if you've used Siri or Alexa, if you've seen an Amazon recommendation, if you've seen an ad that was probably given to you by artificial intelligence, and some things you might not even know about. If you put in an application for a loan or a background check for a rental agreement, those decisions might have been made by artificial intelligence as well. You might also think that, we're close to seeing the artificial intelligence that we see in the movies. So let's look at an example from the Consumer Electronics show last month. This is Amica. It was a robot designed by a company in the UK called Engineered Arts. Let's take a look at an interaction.
I see your rabbit ears.
Yes, you do.
Hello there.
Do you have a boyfriend?
I do not have a boyfriend. Are you asking for a friend?
I'm asking for me.
I see. Unfortunately, I am not on the market. Robots do not have relations. Do you have a boyfriend? I'll take that again.
Great, so obviously that was pretty impressive, maybe a little creepy at the end with that stare. And you might be thinking, wow, AI is really impressive. I want to spoil something a little bit. It's not actually artificial intelligence that is making those responses. Those responses were a human behind the scenes telecommunicating through this robot. But you could think, well, we can just put Alexa or Siri in this robot, and we've got the robots that we see in movies. Movies like what we saw today, or Terminator, or if you like, The Matrix. And all of these depict human-like or super intelligent artificial intelligence. Artificial intelligence that's so smart that it decides, these rules that the human programmed for me, they're no good. And they decide to overthrow the humans. It's pretty scary stuff, huh? Fortunately, we don't actually have to fear that kind of artificial intelligence. That doesn't mean we have nothing to worry about. So today, by the end of this talk, I want you all to understand what AI is that we have today, what are the risks that we're already facing and affect us and our society, and what we're doing about it. And I know robotics plays a big role in AI, and even when I was thinking about what to talk about here, there's so much in the fields of robotics and AI, so I really had to bring it down to scope. So I'm just going to talk about artificial intelligence, not about robotics. And I'm going to talk about AI in terms of what we see in the movies and what exists in the real world. The AI that we see in the movies is called general artificial intelligence. It's this general intelligence that can do any cognitive task, anything a human could do, any intellectual task. That does not exist. What does exist is called narrow artificial intelligence. That's artificial intelligence that's designed to complete a specific task. Now, there's lots of definitions to artificial intelligence. As was mentioned, I'm the director of a summer program that teaches AI, and the definition that we use is that AI is a discipline concerned with the designing of computers to make predictions and decisions. And within that, some of you maybe have heard the term machine learning. Show of hands, have we heard the term? Yeah. So machine learning, abbreviated ML, is an approach to artificial intelligence, and it's specifically an approach that uses data in order to make these decisions. Now we're going to take one more step deeper into this. Within machine learning, there are lots of different types of machine learning. I'm just going to talk about one today called supervised learning. And the reason I'm just going to focus on supervised learning is the vast majority of AI that we see in the world today, that you see in the news, or that we're actually interacting with maybe on a daily basis, is supervised learning. So when I use the term supervised learning, when I use the term machine learning, you can just think AI. For right now, just consider them to be the same. And like I mentioned before, the AI that we have today is narrow AI. It is artificial intelligence that is designed for a specific task. And with supervised learning, that task generally always takes the same structure. And that structure is that we want to create a machine learning model, an AI, that takes an input, for example, an X-ray image, and gives us a prediction as to a label on that, such as if a bone in that image, in that X-ray, is broken or not. And so in order to do this, the field of AI is focused on creating a good model here. And the old school version to do this is that computer scientists would try to write every rule, in the broken bones, look for a shape that looks like this, or a discoloration that looks like this. Now, we use data. That's why we're able to do the things we do today, because we have the processing power to process all of this data. This does not mean that humans are no longer involved in this process. They're actually very involved in this process. So in order to create a model like this, the first thing that a designer or a team of designers has to do is ask a question. And this question should be useful in the world. And actually, by asking this question, you're saying something about the world. It should also be something that can be answered using data. So in our example with the X-ray, the question is, can we predict whether a bone is broken or not by looking at an X-ray? Pretty basic question. And like we said, we want to answer this question with data. So step 2 is we've got to collect a bunch of data. This data has to be both the inputs and the true outputs for our system. So it's got to be a bunch of data of X-rays of bones that are already labeled as to whether or not the bone in that image is broken or not. And there's a ton of considerations that have to be considered when collecting all of this data. Who's represented by the data? Where is the data from? Who labeled this data? Who got to decide whether that bone in that X-ray was broken or not broken? And so once we have all of this data, the last thing to do is where the learning actually happens. And I put that word in quotes because it's an overloaded term that makes us think that AI is magical and human-like. What learning means is that we are training a model. And again, training, learning, these words might not mean anything to you. What it means is the designer is going to choose an algorithm. As you can see here, there are many different types of algorithms that the designer can choose, even within the narrow scope of supervised learning. But the algorithm is going to process all of the data that was collected to find statistical patterns. Patterns that are similar among all of the images that are labeled broken, for example, versus patterns that are all similar in the not broken images. So they can use those statistical patterns to predict from input to an output whether an image is broken or not. And that's it. That's AI. So a summary of that. First, you have to learn your model. That is, take a bunch of data, take an algorithm, and process that data to create a model. Next, you take that model and you throw it into the real world. And here, you're deploying it where it is given a new input, one it hasn't seen before, and it's going to make a prediction, hopefully an accurate one, as to what the correct label is or should be. And like I said, supervised learning exists all over the world, whether you know it or not, and it affects our daily life. So for example, how many people here have Netflix and watch Netflix? Wow, even more people than they thought interacted with AI. Yeah. And should I ask how many actually pay for it themselves or no? Okay, we've got one. So Netflix uses machine learning in order to give you the recommendations of what shows to watch, what movies to watch, what you should watch next. And these recommendations matter. Netflix estimated that 80% of the time, the clicks that users, the decisions that users make, the clicks they make, are from the recommendations, not from them using the search functionality. So the machine learning model here takes as an input movies you've watched in the past and maybe the ratings you've given those movies. And the output or prediction is the ratings of movies you haven't watched. You could think of it also for an individual movie, whether or not it should be rated as, or predicted that you're going to watch it or not going to watch it. Another example here that I love is this caption that, AI headlines love to really grab you. The pastry AI that learned to fight cancer. Makes it sound like AI is pretty smart. So let's take a step back and think what's actually happening here. So a model was trained that can take as an input an image of a pastry and give as an output the type of pastry to label what type of pastry is in the image. Now, if you took that model and you gave it a image of human cells in hopes that it's going to tell us something about cancer, what do you think the output would be? Pastries, exactly. That's what the model knows how to do. It's just going to tell you this image of human cells looks like a certain pastry, probably a Danish. So what actually happened here? What is this article actually about? What actually happened is that the learning process that was used to create the pastry model was found to be an effective process for learning a cancer model. And that is, they had to collect a whole bunch of new data of images of human cells and label all of that data as to whether or not there's cancer or not cancer, or what types of cancer are in it, and then use that same learning process in order to learn a new model that was a cancer detection model, not a pastry model. The last example I want to give you is if you've used Gmail, you might have seen the Smart Compose feature. And so the input to the machine learning that's happening in the background here is a word, a phrase, a sentence that you type, and the output is the words that should come next, a recommendation of how to complete that sentence or that phrase. And maybe you weren't sure what you were going to bring. So a recommendation like this might be like, oh, well, I guess I'm bringing chips and salsa now. So these kinds of things do matter. So all of these examples should show you kind of very tangibly what is happening with AI. What is the type of task that artificial intelligence these days can do? And you might be thinking, whether I bring chips or salsa, or whether I choose to watch Blade Runner or not from a Netflix recommendation, who cares? Do I really have to worry? And unfortunately, there are risks with these systems. There are biases that enter this system throughout the design process. This is already happening and having tangible effects on our world. So, for example, the first type of error you might think of is, what if this prediction that it gives me is wrong? Obviously, we don't want these systems to be inaccurate. But a deeper, even more fundamental problem is that not everyone who's affected by these systems gets the same rate of errors. I'll use an example to explain this. There was an algorithm, a company that designed a model a few years ago that was called Compass, and it was a recidivism model. So it predicted recidivism. It took as an input a bunch of background information on an individual that was up for parole. And the output was a score, a risk score, prediction of high risk, this person is likely to reoffend, or low risk, this person is not likely to reoffend. Now, this type of system can have two errors. The first error is an overestimate of risk. So on the left here, an individual gets labeled as high risk, but they don't actually go on to reoffend. The other type of error is an underestimate of risk. The machine learning algorithm looks at the background of an individual and says, no, they're good. They're not going to reoffend. But it was wrong. They do go on to reoffend. And ProPublica did a study, and they found that there were huge differences in these errors among Black versus white Americans. For example, Black Americans were twice as likely as white Americans to be incorrectly labeled as high risk when they don't actually go on to reoffend. And for white Americans, it was the vice versa. It was almost as if, the algorithm, the machine learning model, was giving white Americans the benefit of the doubt. And these types of errors don't just happen in criminal justice. These can affect decisions made by AI models that are in approving loans or deciding which resumes to accept for a job. And this is just one category of risk. And these are really tangible risks, but there's a whole set of less tangible risks, like representational harms. So there was a study a few years ago that looked at what are the results you get when you Google CEO for an image search. And as you can see here, the vast majority of them were white dudes. Now, you actually had to scroll down to the 70th result to find the first woman. Can we have any guesses of who that might have been? No idea? Doesn't matter. You could say anything. You're not going to guess. It was CEO Barbie. Yeah. Yep. Hilarious and deeply disturbing. Yeah, so if you Google CEO now, you're not gonna, I mean, eventually you'll find CEO Barbie, I'm sure, but you're gonna get very different results because, this was not good PR for Google, so they went in and they fixed this problem. But they fixed this instance of this problem. They can't go to every search query that's possible and hand fix all of these results. There are deeply embedded issues here. And not just in, this is one example of a representational harm, specifically underrepresentation. There's been examples where AI is stereotyping or AI is denigrating people. Like one that was learned off of Twitter data and became racist real quick. So the last example of a risk that I want to talk about is one that's kind of inherent when we try to use a purely technical solution to try to fix a really complex social problem. And I want to use autonomous vehicles as an example. And so autonomous vehicles use machine learning to predict what humans in the world are going to do. So it uses it to predict what's a pedestrian going to do or a human driver going to do so that it can act accordingly, so it can act safely. But whenever that autonomous vehicle gets put into that system, the fact that it is there, its presence and its actions change the behavior of the people involved. Uber found that its self-driving vehicles were being bullied on the streets. Pedestrians, other drivers, you can think, if you know that's an autonomous vehicle, it's programmed to get out of my way. I'll just merge whether there's room or not, and it'll move. And this problem doesn't just show up in autonomous vehicles. I want to compare, for example, our X-rays to our recidivism example. With X-rays, with the X-ray machine learning model, it's observing broken bones, X-rays of broken bones. No matter what prediction it makes, bones are going to look like bones. Bones 10 years ago, bones 10 years from now, they're going to pretty much look like bones. And more importantly, the predictions that this model makes is going to have no impact on what those bones look like. The same is not true in recidivism. Recidivism isn't merely, this machine learning model isn't merely observing the criminal justice system. It's not merely observing crime. It's participating in the parole process. It's participating in this system. And so its actions have an impact on the system that it's trying to make predictions about. And this dynamic feedback loop is something that, this tightly defined task that we talked about with narrow AI is not really made for that, or it's not its strength. So you should see with all of these examples that there are risks, real risks for real people in the real world that can change people's lives. And these could be from disparate errors, from representational harms, or just from the assumption that a technical fix will solve our complex social problems. There aren't any easy fixes, but there are things we can do. And there are things that I'm doing, as you heard a little bit about. And so I want to talk about specifically 3 types of fixes and approaches to reducing risk in AI. The first is a technical fix. And this plot here shows how the increase in studies on fairness in machine learning. And a decade ago, everyone was like, pish posh, who cares about this? This is not a problem. And then all of a sudden, when you start seeing CEO Barbie pop up, you're like, okay, maybe we should do something. And so technical fixes, one of the common approaches, for example, is to define a mathematical definition of fairness. So with our recidivism example, maybe the definition is that our rates of both of our types of errors should be equal for whites versus blacks. And then you have to design a bunch of algorithms, make sure your data is correct so that you can actually create a model that adheres to that definition. These types of technical fixes do address some of the problems, especially problems that you have with data and with algorithms. But some notions of fairness in the real world aren't really mathematical. Take the notion of due process. You can't put a mathematical definition on that. And furthermore, the issues and the problems that technical fixes address are only in the data and the algorithm. And it doesn't even address all of them there, but only some of them. We even skipped step 1 in our whole process. Step 1 was asking the question. And asking the question is a super important part of the process. And that's why, for me, the second thing I'm involved in is getting better education and representation in AI. And that's why I'm the director of the AI4ALL GRASP program. We teach underrepresented students from Philadelphia area high schools, and we teach them the basics of AI. We give them hands-on experience with AI, And we give them the tools and the career development they need to become future leaders in this field. Because we need diverse voices so that we can ask the right questions. Because these questions matter a ton. It's the questions that get asked that determine research directions, that determine which algorithms get designed and get developed. Again, let's look at the recidivism example. The question that was asked was, can we predict the likelihood that an individual reoffends? Maybe we could have also asked, can we predict whether an intervention is effective in preventing or reducing the likelihood of reoffending? You could possibly get data on that to try to answer that question. And those two questions lead to a parole process that looks very different, and outcomes for real people in the real world that look different. And that's why questions matter. The last thing that I do in order to try to reduce the risks of AI is science policy. I believe policy is important because policy is where we ensure that responsibility and liability for when these things do make mistakes is there, for when discrimination from these happens, for when there are disparate outcomes due to these technologies. We need to ensure that we track down these, that there is oversight of these types of harms. And so it was mentioned earlier, for example, that with this organization that I work with at Penn called the Penn Science Policy and Diplomacy Group, I went to the United Nations and I got to speak on the floor of the UN to representatives from around the world about the very issues and risks that we're talking about today. In addition, we as a group, we publish policies and write policy memos about myriad topics. So we've written policy memos about AI's impact on jobs, about the bias in AI in advertising for STEM education programs, and most recently on AI in housing. So there's a long history in the United States about discriminatory housing practices and whatnot. And now landlords and the like are using algorithms. So we did research on the prevalence of these kinds of systems, the possible harms they're causing. And then with all of these memos, we engage with policymakers at the local, state, and federal level to ensure that they're aware of this. We can lend our expertise, share our findings, discuss what can be done to ensure that the regulatory measures that exist, there are already plenty of anti-discrimination laws, for example. We just have to ensure that they keep up to date with technology. Now in Blade Runner, one of the quotes that stuck out to me was what Deckard said. He said, replicants are like any other machine. They're either a benefit or a hazard. Now, I don't believe that AI is either a benefit or a hazard. You should have seen today that through all of these examples, AI has the potential to improve systems like healthcare, but it also comes with risks of exacerbating or creating inequalities in our world. So next time you see AI in the headlines, whether they're overhyping it or using it to spread fear to get new clicks, take a step back. Think about supervised learning. Think about the models and the types of tasks and ask yourself, what is this AI actually doing? What prediction is it trying to make? Also ask, who got to ask the question? Who's benefiting from this? Who are the people who designed this? And importantly, think about who are the people who could bear the brunt of any bias that could happen in this system. Thanks. Yeah, we're going to take some questions. I think we have a second mic here that can be passed around so everyone can hear you.
I have a question. Can we not have his mask on? I don't see the point.
We're going to take AI-related questions only.
I have trouble.
Oh, he has trouble. Question. Here we go.
I'll make sure I speak louder for you. Sorry about that.
You're doing great.
Thank you.
Hi there.
Hello.
I teach high school, and
Great.
I would like if you could tell me what the secret sauce is in the TikTok algorithms that makes them so deeply addictive to every student that I teach. Thank you.
Yeah. If only I knew. So, companies like TikTok, Facebook, whatnot, the underlying model is the same, right? the input is the history of things you've watched, and the output of these models is the recommendation of what to watch next. So it's the next thing on Facebook, on Instagram, on whatever the next TikTok that is shown to you. It's the same basic algorithm. There's a ton of work that goes into creating that model that maps from the inputs to the outputs. And for social media organizations, they have social scientists, psychologists, all of them. So I would say that you have to ask them. Once you know that special sauce, if you want to make that system, you come to me, and I'll tell you how you make that system, given that special sauce. Eliminate that special sauce. Okay, great. So that, I would say, is a policy issue, probably. Yeah, question in the middle here.
Is there any evidence that AI is being used in politics, and where, if it would be the first place that it would be used?
Yeah, excellent question. So where AI is being used in politics. One, I would say, I don't know that I can point you to evidence right now, but I would say absolutely they're being used. Especially because even in the past, before the hype of AI, political strategists, political campaigns use whatever data analysis tools they can get their hands on in order to use their money to equal the most number of votes that they can get. And so the example that comes to mind would be targeted advertising. And so targeted advertising is about finding and advertising to the smallest number of people that is most effective. You want each dollar that's spent on advertising to lead to as many votes in favor of you as possible. So I would say they're probably investing money into the algorithms that determine who on Facebook should get targeted ads for my campaign. And not just any ad, the ads themselves are targeted to the individuals. So whenever you see an ad, two people could see an ad for the same thing, and they're two different ads. Sometimes even on Netflix, you could see two different art labels for a movie because they're designed for you. And maybe not you as an exact individual, but there's a bunch of options to choose from, and it's using the one that it thinks will get you to click on the movie. The highest chance of clicking on the movie. A great question. And we've got a bunch coming from this side.
I was wondering if you think we're relying too much on analytics. I'm thinking about like the sports, how they use that a lot in football, and if that's taking away from the human factor of decision making.
Yeah. So, yes. I would say yes. I think, for example, and I'm not the only one who thinks this, that there needs to be, especially in AI practitioners, STEM education generally, a stronger focus on critical thinking about humanities. And this is actually something that the CEO of IBM said. If anyone's going to be, pro everything STEM, it's going to be the CEO of IBM. So I think there's a lot of evidence that there needs to be this social aspect, and that there is. Sorry, I'm not sure what I did there. So yeah, there needs to be. These are social. Most of these things are social problems. Like if all you care about is taking an image and needing to classify or predict what is in that image. Just the fact that you're classifying things has a long social history of politics and racism and so much involved in that no, it's not just technical fixes. We do need social approaches to this. We can't just do data analytics and think it's going to answer all of our questions. Yeah, we've got another one over here.
All right, I'm going to hit you from the other side. I played with perceptrons in the 70s. I played with three-layer neural nets in the 80s. I've been an HPC for the past 20 years, but from a systems side rather than an application side. So my question for you, two-parter here, is there actually a difference in fundamental math in the modern neural net learning models compared to what there were before, or is it just a matter of scale? And the follow-up to that is do you think the current approach gives us a path towards a general intelligence?
Awesome question. So we've got an AI practitioner here, probably like a professor in AI. He knows what he's talking about.
I'm one of the monkeys you asked to code.
Oh, okay, great. Unfortunately, as a Ph.D, I have to do all my own coding, so I don't have any of those monkeys. So the first thing that he's talking about is perceptrons. Perceptrons are a type of model. So when we talked about, let's look at this one. All of these different algorithms at the bottom, they bring structure to the type of model that you are training. They bring structure to how you analyze the data, how the algorithm analyzes the data. One example is called the perceptron, and it's inspired by the idea of a neuron. I wouldn't say it is designed to mimic or replicate. It's just inspired by it. It's just an example of one. And it was created, like we said, back in the 70s, 80s. It's been around for a long time. If you've, show of hands, who's heard the term neural networks? Deep neural networks, deep learning, any of those? If you've heard any, raise your hands. Okay. What that is rather than one little perceptron, so let's take, for example, none of these are actually perceptrons, but on the right here, if you imagine that each of those dots, each node is a perceptron, it's one of these little models. A neural network is a network of these perceptrons, a bunch of connections. And what the machine learning algorithm is doing is, while it's also finding the patterns between inputs and outputs, it's finding the patterns between all of these neurons as well. And so yes, it is really a matter of scale. And the reason we can do so much now that we couldn't do when the fundamental theory was created back in the 70s and 80s is because we have the processing power to do it. And so now we have, GPUs, if you've heard of graphical processing units. Our computational power allows us to tackle some of these problems. And because to take a half step back, when we talk about collecting data, I'm not talking about, okay, go get me, 3 x-rays of a foot and label 2 of them as broken. I'm talking thousands, hundreds of thousands, millions of images. In order to process that data, you need a lot of processing power, and it's taken decades for our superconductors or our semiconductors to get, technology to catch up to the point where we can process all of that data and do things with it. The second question is, okay, great, we have all of this processing power. We possibly have, processing power beyond our wildest imagination. If you listen to what they say about quantum computing, right on the horizon. I don't think, the question was, does this mean that this is going to get us to artificial general intelligence? Remember, what we have today is artificial narrow intelligence. Among all the experts, there's a lot of different predictions about whether or not we'll see artificial general intelligence in our lifetime, in 10 years, in 50 years, never. It's pretty much all over the place. One thing that is more generally agreed upon, though, is that the steps from here to artificial general intelligence are not linear. They're not even known. It's not about, okay, let's just combine things. So to get from the perceptron of the 80s to the neural networks of today, it was putting things together. And not just putting them together makes it sound really simple, it's really complex. But it's not that step to get to artificial intelligence. Artificial general intelligence, is going to require new fundamental ideas. And importantly, we don't even understand our brains and the brains of animals. There's a lot of work that needs to be done on that front and a lot of unknowns of how do actual real neural networks, biological neural networks work. So no, I don't think we're a step or steps. I think there needs to be a transformational change in the underlying methods and understanding of biological systems of the like. Yeah, an excellent question. We had another question in the back. We'll work our way toward the front here. I see more hands.
I may be too far away. There we go.
Okay. Hi, I think I heard about that recidivism algorithm a couple years ago. I think one of the problems was that a lot of times that's proprietary information that's purchased from a private company, and I think New York had purchased it. So it was hard for people who were caught up in the problems of the system, the biases and the prejudices, to fight back. Is that one of the things you're doing to make it easier for people who have a problem with those proprietary systems to fight back and get their day in court?
Yeah, absolutely. So that's very astute, very an amazing point that one of the issues and one of like the risks and whatnot that, I had to narrow this presentation down. There's, like I said, a million topics, and there's a whole side of risks of AI where it comes to not knowing exactly how or why it's making the decision that it's making. Transparency of the algorithm, whether it's under, behind the wall of like private companies owning it and us not being able to see it. I do think the policy space is how we approach that. There are some technical things in that realm on like, how do you ensure that you can explain why a decision was made? There's a whole set of laws about the right to explanation. So if you've heard of GDPR over in Europe, it's all about like, if I get a loan denied, I should know why it was denied. And if you're using an algorithm, especially an algorithm like the one that looks on the bottom left here, the deep neural networks that are just like a mess of numbers, even the people who created it can't look at that and say, oh, it was because you didn't pay your last payment. That's why you didn't get the loan. There's really no way of knowing. There's some methods that say, oh, well, like you look similar to these other people, and those other people, generally don't pay their stuff on time, so that's why. But it's not really an explanation. So I think the policy space is the approach to that. I don't think it's happening at the pace that we need to, that recidivism example being a perfect example of that. I would add one more thing on top of that problem that is an issue, in addition to transparency and being able to fight back, having due process, all of these things, is that I talked a little bit about the definition of fairness that you could put in that system. There's a lot of arguments for a million different definitions of fairness that could be had. And all of these definitions of fairness usually act on the aggregate. They are, are you fair on average over all of these? That says nothing about whether your personal experience as an individual who's affected by this algorithm, whether or not that was fair, and whether you have the chance to fight back against that decision. Yeah, thank you for that question.
Thanks for your great presentation and your intelligence tonight. Cookies are something they're part of the data, correct? That is being collected for good and for bad. The bad may be to sell you more than you need, or to make the corporate more richer. So how would you advise us our vigilance on that?
On whether or not you should accept the cookies?
Yeah, I mean, you get asked all the time.
All the time.
Yeah.
All the time. So, should you have cookies? It depends. It's personal preference. So again, when it comes to privacy, there are a lot of different views of privacy, both on individual levels, cultural levels. For example, countries in the East have very different attitudes towards privacy than we do. Some make the argument that, privacy and hackers and all of this, like as an individual, like who cares? Unless you're a state actor or you're a government or a company and you're worried about corporate espionage, like not really a worry. The problem for me is not as an individual. Like as an individual, whether you accept the cookies or not, I don't think really is going to have a measurable impact on your life. Or at least the chances of it are pretty low. The problem is across everything. So it's not that, it's like with the Netflix recommendations. 80% of the time users use those recommendations. One way to look at that is you could say, wow, Netflix did really good at predicting what people want to watch. The other way you could look at it, you could say, wow, people are really influenced by whatever Netflix is going to say. And it's obviously not one or the other, it's a mix. And it's the same thing with cookies. Those cookies lead to ads, and what they do with these ads is pretty incredible. And again, it's all part of, it's that dynamic loop that I see you showing. It's all part of that system, that feedback loop, the TikTok that just keeps you engaged. And so watching one more TikTok isn't a problem. Taking your cookies one more time or giving them your cookies isn't a problem. But societally, the impact that it does and the attention that it grabs and things that it pushes forward, it's one view that I really like is about power. One thing we can think about with AI is who does this technology give power to? So when we talk about cookies and when we talk about TikTok and when we talk about these technologies, we can ask ourselves, are they giving power to the more powerful? Is this kind of power exacerbating the gaps that exist in our world? The wealth gaps, the knowledge gaps, all of these gaps. So on an individual level, if it's easier for you just to take the cookies because, you want to be good and you say, okay, decline the cookies, and then it wants you to do like 6 other things, so you just accept that anyways. It's probably not bad, but I think at a higher level, at the policy level, at the societal level, that's where things need to be done.
Thank you.
Yeah, a great question.
All right, last question. Who's got one? This gentleman right here.
Going back to what you were saying earlier about how we don't understand the human mind or animal minds, are there any direct links between those fields of study and this machine learning study? Is there any people who are working directly with both, or are they still very separate fields of study and very separate processes?
Yeah, absolutely. Awesome question. So, yes, there is definitely relationships between the two. So the one most common is relationships between neuroscience and artificial intelligence. One distinction that, again, I would reiterate is with neural networks that we were talking about. Oftentimes what is done in artificial intelligence and with technical systems is that they are bio-inspired. So they are inspired by these systems. If you think about Elon Musk talks about Neuralink and stuff like that, that's really trying to find where the studies of the brain and technology actually come together. Most of the work, I would say, is inspired from one to the other, but a lot of ideas flow, especially through neuroscience and artificial intelligence, because not only are we as artificial intelligence designers interested in everything we're learning about the mind, a lot of people who are interested in studying the mind look to artificial intelligence as ways to study the mind. You can think of it almost as a thought experiment that's a little more tangible. So I would love to see more there, because I think it's a very loose relationship right now. There are some cool studies. One I was talking about earlier was they used actual neurons and tried to teach it Pong. And so the idea is you can give electrical impulses to real neurons, and that either creates connections or doesn't create connections. And so there's some studies where they're taking toy problems that were originally used to develop AI algorithms, and now they're testing can we do this with biological neural networks rather than artificial neural networks? So there's definitely some overlap there. Great, thank you everyone.
Thank you so much, Matthew. Round of applause. Thank you very much for coming tonight. We appreciate it, and we'll see you at the movies real soon. Thank you.